Okay, so let us start. So, hello and welcome to week 11 of the Algebra 1 course offered by NPTEL. I am Subhajit Das, one of the TAs for this course, and each week we keep solving some problems from the previous year assignments. So, I do hope that you are attending Harish's sessions. He solves some problems and I solve some problems each week. So, yeah, so let's start. So this is week 11 as I mentioned. So this week you have studied some newer notions like equivalence of matrices or linear transformations, and you have also seen the Smith normal form of a matrix, and you have, most importantly, you have seen the Noetherianness of modules, and you have seen some important applications or uses of the Noetherian condition. As you already know by now that the Noetherian condition is basically a finiteness condition, right? So it's a very important and a powerful. It was a very important and powerful idea. It is named after Amy Noether, a famous mathematician, lady mathematician. So, and even though right now you have seen three important equivalences concerned with the Noetherianness condition, but yeah, it's much more deeper than it appears to be. So the person who actually came up with this had had a very broad insight. So yeah, so let us start solving the problems. So let us look at problem 1. So let me read it out first. So assume that R is a commutative ring which has identity, and let A and B in GL and R be such that A is equivalent to B. So now we are not taking A and B to be arbitrary matrices, we are taking A and B to be n cross n invertible matrices which are equivalent. So we need to determine whether the following is true, that the inverse of A is also equivalent to the inverse of B. Now this is very easy, of very basic thought will let you know that this is true. So we claim that this is true. Okay, why? So yeah, so as I was saying that this, okay, so let me read out the question again, that R is a commutative ring with identity and A and B are in GL and R, which are, that is, A and B are n cross n invertible matrices such that A is equivalent to B. So we need to determine whether A inverse is also equivalent to B inverse. So as I was saying that this is indeed true, that is A inverse and B inverse are equivalent, and it's very easy. It just follows from the definition of what equivalence of matrices is, right? That we know that A is equivalent to B implies that there exists invertible n cross n matrices P and Q in GL and R such that B is equal to P A Q, right? Is that okay, Ravi?
Yes, sir. Correct, sir.
Yes. Okay. So yeah. So now we know that A and B are in GL and R, they are invertible, and at the same time P and Q are by definition invertible. So that means we can basically take inverses on both sides. So this will imply that B inverse is just P A Q whole inverse, right? And what is that? P A Q whole inverse is just Q inverse, A inverse, P inverse. So now again Q inverse and P inverse are both matrices in GL and R, right? And this therefore implies that A inverse is equivalent to B inverse. It's as simple or as easy as that. Okay. So the first problem is very easy. So basically what this says is that taking inverses is well behaved with respect to equivalence of matrices, right? So let's talk about the next problem. This is again easy. These are just computational problems. I am not much of a fan of problems of this kind, but anyways, the Smith normal form is a very important form. It all reduces to how much you can simplify your matrices. You can bring down your matrices to a much simpler form. But you need so in such a way that you some properties of the original matrix are still retained, right? So this is what the Smith normal form is all about. Next week you will be studying the rational canonical form and the Jordan canonical form. So yeah, we'll see. So anyways, so let us compute the Smith normal form of this particular matrix x square x minus 1 x square over zx. Now during the session this week, if I am not very wrong, then you were actually introduced to an algorithm to do so, right? You are given some matrix, you have an algorithm so as to obtain the Smith normal form for this matrix. So we are going to do the same, okay? So let us just write down the matrix x square x minus 1 x square, right? So what we want to do is we want to apply the elementary row and column operations, two of them, right? So that we can reduce this matrix to the desired form, which is something of this form d1 0 0 d2, right, where d1 d2 are elements in zx and d1 divides d2, right? This is the form that you want to achieve. So you want this, and yes, d1 must divide d2, and we know that this form is actually unique by up to multiplication by units, okay? So it might, this given matrix x square x minus 1 x square, this might also go, you can also arrive at a form e1 0 0 e2, but you need to know this, that I mean this representation will be unique up to multiplication by units, that is d1 and e1 will be associates, and as well as d2 and e2. Anyways, so we write down the matrix x square x minus 1 x square. So we look at the element 1 1, right? 1 1, we look at the element in the 1/1th position, right? We want to apply the division algorithm on x minus 1, taking the divisor to be x square. Now x minus 1 has degree smaller than x square, right? That means that x minus 1 is x square times 0 plus x minus 1, that is x minus 1 is the remainder. So in such cases, when there is a remainder, we know we need to switch, right? We need to interchange the rows. So how should I, what color? Yeah, okay, so let me use this color only. So we just interchange the column 1 and column 2, right? So C1 is interchanged with C2, okay? So what you have now is x minus 1 x square x, right? So again we want to apply, okay, so again we want to apply, so x minus 1 you have x square here, you have x square here, and you have x here. Again we want to apply the division algorithm now. So basically what we want is, we want a 0 in the 2 1 position and we want a 0 in the 1 2 position, right? So this is what we want to achieve. So what do we do is we apply the division algorithm on x square and x minus 1. So x square is just x minus 1 times x plus x, right? So what you now do is take column 2 minus, okay, yeah, that is you want to change C2 to C2 minus x times C1, right? Note that the coefficients are from zx, right? That is, x is a valid coefficient when you are applying this elementary row operation or column operation. So take C2 minus x times C1. What you arrive at is, so you write C1, which is as it is, and x square minus x times x minus 1, which is x square minus x square plus x, right? That is, you have x here, and x minus x times x square, right, which is x minus x cube, isn't it? Am I correct? Can you just verify and let me know?
Yeah. Yes, sir. I'm getting.
Yeah, okay. So x square minus x into x minus 1, which is x square minus x square plus x, right? And x minus x times x square, right, which is x minus x cube. So now after this, so now we have this, and yet again we can apply the division algorithm on x minus 1 and x, right? Oh, yeah, maybe I am a bit wrong here. I didn't apply the division algorithm properly, did I? So yeah. X minus 1 is, yeah, you can still divide, no, x square minus x minus, so this is x, and you take plus 1, right, which is x minus 1 minus, so this is 1, right? Yeah, I should, yeah,
Yes, sir. This is correct.
yes. So c2 minus x plus 1 times c1, right? This is what we want, and therefore the new matrix that we arrive at is this, right? That is, you have x minus 1 x square here, and x square minus x plus 1 times c1, so x square minus x minus 1 times x plus 1, right? And what is this? This is x square minus x square minus x square minus 1, so you have plus 1, right? So you have 1 here, right? Isn't it? Yeah. So what you have here is x minus x plus 1 times x square, which is x minus x cube minus x square, right, Ravi? Did I do it correctly?
Sir, at 1, can we just check?
At 1, so c2 minus x plus 1 times c1 I took, right? So it's correct, right? Because c2 is you have x square minus x plus 1 times x minus 1, right? So this is x square minus 1, right? So this is x square minus x square plus 1, right? That is 1, right?
Okay, sir. Okay, correct.
And in the second, I mean in the 2 entry, the 2 entry is hopefully correct as well, right? So you have x here, x minus x square times x plus 1, right? So x minus x cube minus x square, yes. Okay. Now what you do is, now this is 1 is your remainder, so now you are again going to interchange it. Since it's non-zero, you are again going to interchange, so you again take use this elementary operation, c1 and c2 are interchanged, and what you have now is 1 x minus x cube minus x square, you have x minus 1 here and you have x square here, right? This is your matrix now. Yes, so after this, so what you are going to do is, it's very easy. Now you want 0 here, right? So what you do is you take c2 minus x minus 1 times c1, right? Because x minus 1 is 1 times x minus 1, that we know, we have applied the division algorithm. The remainder obtained is 0. So take c2 minus x minus 1 times c1. So what you have is 1 0, and you have x minus x cube minus x square here. So let me write it with some space, and you have x square minus, okay, so I need to write this down. So you have x square minus x minus 1 times x minus x cube minus x square, right? So just bear with me, I am horrible with calculations. So this is 0 and x square minus x minus 1 times this. So you have x square minus x square minus, so x square minus x to the power 4 minus x cube, right? And then you have minus x plus x cube plus x square, right? And what you have now is x cube and x cube get cancelled, so you have 1 x square and minus 2 x square, so minus x square you have, right? So you have x to the power 4 first, and you have minus 2 x square, so x square minus x square plus x, right?
Yes, sir. Yes, sir. Correct. Same
Okay.
I got.
Okay, thank you. And finally, so we have applied this, so we have obtained 0 here, right? Now we want to make the element in the 2/1th entry also 0, and it's easy. So what we do is you take R2 R2 to R2 minus x minus x cube minus x square times R1, right? So you take this and what you arrive at is this particular matrix, which I am going to write in red because now we have obtained our desired form 1 0. You have 0 here, and this is the same thing, x square 4 minus x square plus x. Okay, so the Smith normal form of the given matrix is 1 0 0 x to the power 4 minus x square plus x, and then we are done. This is our required Smith normal form. Okay, so let's move on to the next problem. So I believe this kind of questions were also tackled in the sessions this week. So we already know now that if we are given a vector space V and if we are given a linear transformation or a linear endomorphism rather from V to V, that is a homomorphism from V to V, then we can suppose the original vector space was V over a field F, then you can put an Fx module structure on V, right, using that linear transformation. This is kind of a reverse question or a question in the converse direction. Basically what you are given is an Fx module, clearly MA written here, or clearly Ft over Ft modulo ideal generated by T square direct sum Ft modulo ideal generated by T square. This is clearly an Ft module. So you need to find one linear transformation A such that the Ft module structure induced on this vector space is basically this Ft mod ideal generated by T square direct sum Ft mod ideal generated by T square. You just need to find one linear transformation which satisfies this, right? So first of all, can you tell me what should be the dimension of the matrix? What should be the order of the matrix?
Sir, 2 we can take now.
No,
2 element 4.
Yes, 4, precisely 4. Why? Because the given vector, given module, whatever it is, as a vector space over the field F, it clearly has dimension 4. No, Ft modulo ideal generated by T square has dimension 2, and if you take direct sum with itself, it should have dimension 4. So the matrix should have dimension or order 4 cross 4, right? So what is first of all the module Ft module structure on Ft modulo ideal generated by T square direct sum Ft modulo ideal generated by T square. So Ft is a module over itself, Ft is an Ft module. I take the ideal generated by T square, that is a submodule of Ft, right? Now what you do is you take a quotient which is Ft modulo ideal generated by T square. This quotient is also a module on Ft, right? What is your module structure? You just multiply, right? I mean, so take any scalar which is an element of Ft, that is which is a polynomial, and take any element in your module, that is in this quotient, that as you know is basically a coset, right? So let's say Px you take to be your scalar, and let's suppose you take this particular coset T square plus Qx. So what is this? This is just T square plus Px Qx, right? Isn't it? This is your module structure on Ft mod ideal generated by T square, right? Right?
Yes, sir.
So now you are taking direct sum with one more Ft modulo ideal generated by T square. So basically your scalar multiplication is just component wise. So this is your module structure, Ft module structure on this direct sum. Anyways, so what you now do is, we know that what was your Ft module structure induced by linear transformation. So basically suppose T maps V into V was your endomorphism of V, and what you did was you defined the action to be x dot any vector V is just T of V, right? And then you extended linearly using the fact that P of x dot V was defined to be P of T acting on V, right? This was basically your Ft module structure, right, induced by T. So what I'm trying to stress at is basically this, that the single variable that you have x, or in this case let's say t, I have written it to be t, little t. So little t acts like capital T, right? T dot any vector is just capital T of applied on that vector, right? T dot v is basically that vector onto which the vector v is mapped onto, right, by T, isn't it?
Yes, sir.
Yeah.
Correct.
So that means that we just need to find out the action of little t. Okay. So we fix a basis first of all. So let E1 be, so okay, and what is Ft mod the ideal gen by t square? What is the basis for this? This is basically t square plus 1 and t square plus t, right? This is a basis for this. It's a two-dimensional vector space. You already know that you can apply the division algorithm and all that to check that every particular element here can be represented by these two cosets, right? It's a two-dimensional vector space. So take E1 to be t square plus 1 comma 0. Take E2 to be t square plus t comma 0. Take E3 to be 0 comma t square plus 1. This is just a coset, right? I am taking elements E1, E2, E3 and E4 in this direct sum. So it will look like a pair of vectors. One vector is from the first summand, that is Ft modulo t ideal gen by t square, and the second one will be from the second summand, right? So everything will be a coset. By 0 here I mean that the coset containing 0, the coset of t square containing 0. So I could just write this instead of 0. Okay. So and take E4 to be equal to 0 comma t square plus t, right? So this serves as a basis. I hope it's okay. Now let us look at the action of little t. So little t dot E1, by definition the scalar multiplication will be component wise in the direct sum. So t dot ideal gen by t square plus, I mean t dot this coset comma t dot 0 which is 0, right, which is precisely t square plus t comma 0, right, and that's just E2, right? So take t dot E2. Is there any problem or is it okay?
Correct, sir.
Yeah, okay.
This is fine.
So comma 0 which is just t square plus, sorry, so this is just t square plus t square comma 0, and this is just 0 0, right, because t square is the coset containing t square is the same as the coset containing 0. So t dot E3 is again 0 comma t square plus t, which is t dot which is E4, and finally t dot E4 is again 0 comma 0. So yeah. So now we know what t does to the basis, and therefore we can find out the matrix of we can find the required matrix here, which is the matrix of t, right, little t. How the variable basically acts as your linear transformation. So finding the matrix for little t gives you your matrix A, the required matrix A. So the matrix A is, so just look at what it does to the basis elements. T maps E1 onto E2, right, and E2 can be written in terms of E1, E2, E3 and E4 as 0 E1 plus 1 E2 plus 0 E3 plus 0 E4. So it's just 0 1 0 0. T dot E2 is 0 0, so no need to worry, just put zeros. T dot E3 is again E4, so 0 0 0 1, right, that is E4 can be written as 0 times E1 plus 0 times E2 plus 0 times E3 plus 1 times E4, and finally T dot E4 is again 0. So you can verify this, I mean there is no need to verify, but yeah, you can verify that MA, if you take this particular matrix A, if you start with this linear endomorphism A of your 4-dimensional vector space, then MA will actually be your this particular direct sum Ft modulo ideal gen by t square, direct sum Ft modulo ideal gen by t square. So is it okay?
Sir, this matrix, can you once again explain?
Yeah, so basically so little t is basically a linear transformation, right? You agree with that?
Yeah, correct.
So I basically found out what it does to the basis elements, and you know that to write down a particular matrix, you just need to know what it does to the basis elements, right?
Yes, sir.
So basically what I did is I took a linear transformation and I represented it in terms of a basis. Okay, I took a basis.
Yes, sir. Yes, sir. Got it.
Yeah, I just checked what this linear transformation does to the basis elements, and then I express it in terms of that basis. Every linear transformation can be represented in terms of a matrix, right? If you fix basis for your domain and codomain. So yeah, so this is your required matrix such that MA is this. So anyways, so let us move on. So now the questions are going to be much more interesting than they were. So yeah, so I am as I was mentioning that the Noetherianness condition is a very powerful and very important condition. Even though right now you have only seen three equivalences of Noetherianness, that is a module is Noetherian if and only if it satisfies the ascending sequence condition or ascending chain condition on submodules, which is true if and only if, I mean that is the definition you can take, and this is true if and only if every submodule is finitely generated, and then again this is true if and only if every non-empty collection of submodules contains a maximal element. But there is much more thought that goes into making such a kind of a notion. Okay, so it's attributed to Emmy Noether, and yes, the person who actually came up with this idea had much deeper insights into this notion. Okay, so it's very powerful, very important, and it has been, there are many ways in which this notion has been generalized, and we keep using it in algebra again and again. So it's sort of it's a finiteness condition, right? It reduces something which is very large to something finite. So knowing that every submodule of a module is finitely generated is indeed very it's a very powerful assumption, and there are various applications of this, or rather I should say not applications, there are various what should I say, I mean it's really important. So learning Noetherianness is very important, it's very powerful, very useful as a condition. So anyways, so we need to determine whether this particular statement is true and false. So you start with a Noetherian R module, and you take a surjective R module homomorphism from that module to itself. Okay, so it's an endomorphism. So the claim is that if you take any surjective homomorphism, it will be an isomorphism. So what do you think? Is this true or is this false?
Sir, yesterday we did one similar question like this.
Okay. Oh, okay. Yeah, I guess. Yeah. Okay, that might be possible. Actually, I didn't have many questions this week, so which is why I decided to put this problem. Okay. So, anyways, let's just quickly go through it once again. So, what do you think? This will be true or false?
Sir, I'm not getting it, but
okay. So, it might be a bit surprising, but this is indeed true. So since you have seen this problem yesterday, maybe you can guide me through the solution. So don't worry. Let's go. Let's do this once again. Okay. So M is a Noetherian R module. So first tell me, where have you seen this kind of a statement before? I mean, this is a very true statement that if you take M to be a Noetherian R module and you take a surjective homomorphism from M to itself, then it's an isomorphism. You have seen similar kinds of statements before as well. Can you give me an example where you have seen? So basically you have an object and you take an endomorphism from that object to itself, which let's say is surjective, then it also becomes injective. Where have you seen this?
Sir, in functional mapping we do, no?
Functional mapping. What is functional mapping? Do you know the rank nullity theorem? I am sure you know, right?
Yes, yes, sir.
So there you have seen that if capital V is a finite dimensional vector space over a field F, then taking a linear transformation V to V, which is an epimorphism, that is which is surjective, also basically gives you injectivity for free, right? Just a one line application of the rank nullity theorem. Besides this, you have also, I mean, a much more basic situation you have seen in set theory, right? You can take any finite set X, let's say, and you take a mapping of X into X, which is surjective. So you take a mapping of X onto X, then it is automatically injective, right, by the pigeonhole principle, since X is a finite set, right?
Yes, sir.
So the similar kind of situation is going on here. M is Noetherian, and whenever you take a surjective homomorphism from M to M, it becomes an isomorphism. So let us see how we can do this. We need to use the fact that M is Noetherian, otherwise this is certainly not true. So we need to use this fact that M is Noetherian. So the one advantage of taking an endomorphism here, that is a map from M to M, is that you can compose F with itself. Okay, so observe that.
Sir.
Yes.
Like f of x1 equals to f of x2 implies x1 equals to x2. Like that we can proceed.
No, but we need to show that x1 is equal to x2, right? We have surjectivity to show that it's an isomorphism. What is an isomorphism? Ravi, what is an isomorphism? It's simple, right? It's a very simple definition. A homomorphism which is invertible or which has an inverse is an isomorphism, right? In other words, a bijective homomorphism, since we are doing algebra here, usually an isomorphism is an arrow or is a morphism, is a map, you can say, which has an inverse which is also a morphism, right? So if the morphism is continuous map, so an isomorphism in that case will be a continuous map which has an inverse which is also continuous. But since we are doing algebra, we don't need to assume that the inverse that we are talking about also is a homomorphism. It is free. We get it for free, right? So a homomorphism, if you take a bijective homomorphism, that is a homomorphism which has an inverse as a map, then the inverse map will automatically be a homomorphism. So we can just say that an isomorphism is a bijective homomorphism, right? Isn't it?
Sir, here inverse will exist here.
Yes, that is what we need to show here, that inverse will exist. Anyways, an isomorphism is just a bijective homomorphism, right? So what we need to show is that if we take a surjective homomorphism from M to M, then this map is an isomorphism. That is, this map is automatically bijective, which means that this map is injective, right? This is what we need to show. So what you say that f of x1 is f of x2 implies x1 equal to x2, that is what we need to show, right? That is what precisely injectivity is, right?
Yes, sir.
So we need to show that.
Yeah, the unique image for each element.
No, that's true for any map, but what we need to show is that every element in your codomain has a unique pre-image.
Yes, sir.
Yeah. So first of all, we need to use the Noetherianness condition somehow. So let us see. So one way to show injectivity for a map, for a structure preserving map of algebraic objects, is to show that the kernel is trivial, right? So you can just show that the kernel of f is 0. Okay. So observe that for any integer or for any natural number I, f power I, for a natural number I, kernel of f power I is contained in kernel of f power I plus 1. By the way, by power I mean I am composing f I times, okay, f composed with f and so on I times. So why is this true, Ravi? Kernel of f power I is contained in kernel of f power I plus 1.
Sir, the zero element will be there, no, in F.
Yes, in the kernel, yes, but why do we have this? That the kernel of f power I is contained in the kernel of f power I plus 1. So what do you need to show? Whatever is in the kernel of f power I, that element must also be in the kernel of f power I plus 1. So take x in the kernel of f power I, right? This by definition means that f power I applied on x is 0. F power I maps x onto 0, right?
Yes, sir.
So that means that f applied on f power I of x is also 0, because f takes 0 to 0, being a homomorphism. That means f power I plus 1 of x is 0, which means that f power I plus 1 also sends little x onto 0. It maps little x to 0, right? And that means that x is contained in the kernel of f power I plus 1. As simple as that, right? So that means that kernel of f power I is contained in the kernel of f power I plus 1, right? Okay. So this is true for any I in natural numbers. So we have an ascending sequence, right, of submodules of M. Right? So what is that sequence? So kernel of f is contained in kernel of f power f square, which is contained in kernel of f cube, which is contained in kernel of f power 4, and so on. This is contained in kernel of f power I, which is contained in kernel of f power I plus 1, and so on, right? This is an ascending sequence of submodules of M. Do you agree?
Yes, sir.
And
It is
now M is Noetherian. So what can we say? So since M is Noetherian, or by Noetherianness of M, what can we say? Every ascending sequence will eventually become stationary, right? So everything will become stationary eventually, means that there exists a stage I naught in natural numbers such that after which all the modules, instead of increasing, are actually equal, right? So such that kernel of f power I is equal to kernel of f power, okay, so to help you understand this better, I'll just instead write kernel of f power I naught is equal to kernel of f power I naught plus 1, which is equal to kernel of f power I naught plus 2, and it goes on, right? Isn't it? This is your Noetherianness condition, right? If you take an ascending sequence of submodules, it will eventually terminate, right? I mean, not terminate, it will eventually become stationary, right? So M1 containing M2 containing M3 and so on, if you take any ascending sequence of submodules, then there exists some stage, let's say I, such that Mi is equal to Mi plus 1 is equal to Mi plus 2 and so on, right? The modules, instead of increasing, will actually be equal. That is, a sequence is stationary, right?
yes, sir.
Okay, so now we have this, and this is our pivotal observation, and this is what we are going to use in order to conclude. Okay, so so let's just recall what we wanted to do. We wanted to show that the given map F is an isomorphism. That is, we wanted to show that the map F has trivial kernel, right?
Yes, sir. The element 0 is there.
No. Yeah, but
I mean, the
0 is the
trivial.
only element in the kernel. That is what we want to show. 0 is already in the kernel, that we always know, but 0 is the only element which is getting mapped onto 0. That is what we want to show, right? So let x be in the kernel of f. So assume that little x is in kernel of f. We want to show that x is 0. Now this is where we are going to use our surjectivity as well. X is in the kernel of f, and kernel of f is contained in M. That is, little x is an element of capital M, right? And we know that the map F is surjective. What can we say?
Injective plus bijective, no? Every element will have a pre-image.
Yeah, but why did you say injective plus bijective? I don't know what that means. Surjective means that the image is precisely your equal to your codomain, right? So if you take any element, any arbitrary element in your codomain, then that particular element is that particular element is covered by some element of your domain. That is, there is, given any element of your codomain, there is some element of your domain which is getting mapped onto that element, right?
Yes, sir.
So given any element of your codomain, there exists an element in your domain which is getting mapped onto that element in the codomain. So anyways, we are not going to use the surjectivity of f here. Notice that whatever condition we have obtained, it is a condition starting from the stage I naught, right? So kernel of f I naught is kernel of f I naught plus 1 and so on, right? So since f is surjective, a composition of surjections is again a surjection, right? So excuse me, I just got a call. So okay, maybe I will take that later. So anyway, so since f is surjective, hence f power I naught is surjective. You agree, right? A composition of surjective maps is surjective, right?
Yes, sir. It will give.
Thus, there exists y in M such that f power I naught of y is x, right? There is some y which is getting mapped onto the element x under f power I naught, precisely because f power I naught is surjective. Okay. Now, x is in the kernel of f as we assumed. This implies that f of x is 0, which implies that f of f power I naught of y is 0, which implies that f power I naught plus 1 applied on y is 0, right? Is it okay? Which implies that y is in the kernel of f power I naught plus 1, right? But we saw that the kernel of f power I naught plus 1 is a kernel of f power I naught. So this implies that y is automatically in the kernel of f power I naught, right, Ravi? So this implies that f power I
Yes, sir.
naught of y is 0, but f power I naught of y is just your x, right? So that means x is 0, right? Thus what we can say is kernel of f is 0. Hence f is injective, and since it is already surjective, hence f is an isomorphism of M onto M. That is, f is an automorphism of the module M, and that finishes this particular problem. So this is indeed a true statement, and yeah. Okay. So let's move on to the next problem. So here onwards the questions are not from the assignment, because there were not many interesting problems in the assignment. The first 3 were from the assignment, I mean the first 4, but the fourth one you already encountered yesterday in Harish's session probably. So the next problems are not from the assignment, they are my own. So let's they are very easy, so let's just go through them one by one. I guess we only have 2 more problems. Okay, 3 more problems. Okay. So let R be a commutative Noetherian ring. So you know what commutativity of a ring is, you know what Noetherianness of a ring is. That is, R is a Noetherian ring means that it is Noetherian as a module over itself. So true or false, every R module is Noetherian. So you take the base ring of scalars to be a Noetherian ring. Okay. You need to determine whether every R module over that ring, every module over that ring is also Noetherian or not. So what do you think? Will this be true or false?
Sir, by maybe, yeah, it is true, like by using the commutative property.
No. Commutativity is not that much important here. but this will be false actually. Not every R module is Noetherian if the base ring is Noetherian. So this is false. So let us look at an example, that is a counter example. Take F to be a field, or maybe not F, let's just take Z. Take the polynomial ring in infinitely many variables, Z, x1, x2, x3, x4, and it goes on. Okay, you understand what this is, right? You take the polynomial ring in infinitely many variables. Is it okay?
Yes, sir. Yes, sir.
Okay. So every element here is just a polynomial in infinitely many variables. That is what it is. I mean, it might sound confusing. Every element in here is just a polynomial in sum of the xi's. Okay, finitely many xi's, and the number of xi's, the number of variables or indeterminates are infinitely many, x1, x2, x3, x4, dot dot dot, xn, and so on. Okay. So this is a Z module, right? In other words, this is an abelian group. Now Z as a module over itself is Noetherian, right? I mean Z as a ring is Noetherian, right?
Yes, sir.
Yes, Z is Noetherian. So this is a Z module. We claim that this module is not Noetherian. Now we know that a module is Noetherian if and only if every submodule of it is finitely generated, right? Right, this is
Yes.
one of the
Yes, sir.
one of the equivalent statements of Noetherianness, that every submodule of that module should be finitely generated. So in this case, every submodule of Z x1 up to xn and so on of this particular module should be finitely generated. Now every submodule is precisely a subgroup here, so every subgroup of this should be finitely generated. So take I mean finitely generated over Z here. So take the take the submodule generated by x1, x2, x3, x4, and so on. Okay. So you take the submodule generated by all the variables or all the indeterminates. So yeah, so you take this. This is this finitely generated? Let me ask you.
Sir?
Yes.
Yes, sir. Take the submodule. No, this is infinite. No, sir.
No, we have a generating set here which is infinite, but is there any guarantee? There is no guarantee, right? There could be a finite generating set for this particular submodule that you have taken, right?
Sir, I didn't get this.
So what I am saying is, you take, let's call this x, okay? Let's call this submodule x. This is the submodule generated by x1, x2, x3, x4, and so on, right? Z submodule generated by x1, x2, x3, and x4, and so on, right?
Yeah, correct.
So I am saying that, so what is an arbitrary element here looking like? It looks like lambda 1 x1, let's say, plus lambda 2 x2 plus dot plus lambda n xn, right? Where lambda 1, lambda 2 up to lambda n are integers.
Yes, sir.
So every element looks like this. My question is, it can be very, I mean, we have taken a generating set for this which is infinite, but there is no guarantee, right? You could also have a generating set which is finite, right? Let's say maybe some finitely many elements of this form will give you this entire submodule, will generate this entire submodule. This can happen, right?
Yes, sir. Through infinites, here we can get the infinite there.
That can be possible, but
That
my question
submodule,
is,
yes.
is that possible here?
No, since we have here Noetherian ring,
Okay.
Sir, then the submodule will be generated by a finite element, no?
No. We took a Noetherian ring Z. What was our question? We wanted to show that every R module, if R is a commutative Noetherian ring, we wanted to show that not every R module is Noetherian. So we want a counter example. So that is why we took this particular Z module, which is Z adjoint with, that is a polynomial ring over Z in infinitely many variables. We want to claim that this is not Noetherian, so we just need to produce a submodule which is not finitely generated. We have taken this submodule which is generated by elements x1, x2, x3, x4 and so on, that is generated by all these indeterminates over Z. We have taken this submodule. We are claiming that this is not finitely generated. That is, we can never find a finite subset of this submodule which spans the entire submodule or which generates the entire submodule. That is what we want to show. Okay.
Yes, sir. Correct. Yes, sir.
So that is what we want to show, that this cannot be generated by finite generating set. Okay. So let me just write down the arbitrary elements here. So an arbitrary element. I mean, we could also take much more simpler examples as well. There's no need to go here. Maybe we could also take Q over Z. Z is Noetherian, but Q as a Z module or as an abelian group is not Noetherian. Okay, no, that's a wrong statement, sorry. Q over Z won't work. But yeah, there are, since you are talking about R modules, there are a number of possibilities. We will see one more example. But anyways, an arbitrary element in this looks like lambda 1 x1 plus lambda 2 x2 plus dot plus lambda n xn for some n in natural numbers, for some n greater than equal to 1, and lambda 1, lambda 2 up to lambda n are basically your scalars, that is integers. Okay. My question is this submodule finitely generated or not? We are claiming that this is not finitely generated. You can never find a finite generating set. Why? So suppose, so claim is this submodule is not finitely generated. Why? Assume that this submodule were finitely generated. That is, it would have a finite generating set by, let's say, polynomials p1, p2 up to pk. Okay. Now the point is that p1, p2 and p up to pk, all these are elements in this submodule, right? That means they are polynomials in the indeterminates x1, x2, x3, x4 and so on, right? Now
Yes, sir.
p1, each pi is a polynomial in finitely many variables, right? Since each pi is a polynomial in finitely many variables, you agree with this, right? What is a polynomial? A polynomial has to be, so this is somewhat cyclic, but yeah, a polynomial has to be a polynomial in finitely many variables, right? There is nothing called a polynomial in infinitely many variables. That is, the polynomial cannot go on and on, right? It has to be some, what should I say? It has to be some bounded expression, right? Isn't it?
Yes, sir.
So it can, so it will have, yes.
Variables will be finite there.
So basically the number of polynomials in, number of variables in a polynomial has to be finite. It has to be by a polynomial I mean a polynomial in finitely many variables. Otherwise it's not a polynomial. So since each pi is a polynomial in finitely many variables, and we have only finitely many polynomials here, right? P1 up to Pk. Hence there exists a variable xn, right? Xn which has degree 0 in each of these polynomials, that is, which is not present in any of these polynomials, right?
Yes, sir. Correct.
But then if xn is not present in any of these polynomials, can you write xn as a combination over z of these polynomials p1 up to pk?
No, sir.
Okay. But then xn is clearly not in the submodule generated by p1, p2 up to pk. Okay. Okay, yeah. Yeah, so I mean there are a number of, since it's a very, what should I say, you can take number of different things. We took the submodule generated by x1 up to xn and so on in this problem as an example. You could instead take the ideal generated by x1, x2, x3 and so on here. That would also be a submodule of your z module since it's a subgroup, and you can use the same argument. Okay, so it's not much of a big deal. That is, instead of taking linear combinations over z of x1, x2, x3 and so on, you could take polynomial combinations over z of x polynomial combinations of x1, x2, x3, xn and so on, right? The same argument will keep on working. Anyways, I hope you understood this, okay? But then xn is not in this. Okay, so let me just write something here, okay? So let S denote the submodule generated by S. Okay, this is just for your notation. Okay, so that people don't confuse it with the ideal generated by something. So let S denote the submodule generated by S. Yeah. Yeah. But then xn is not here, okay. But this is a contradiction, right? Because we assume that these finitely many polynomials actually generate your entire ring, right? I mean entire module, right? Is it okay?
Yes, sir.
Yeah. So this is a contradiction. Hence the submodule generated by x1, x2, x3 and so on is not finitely generated. Hence z, x1, x2 and so on is not a Noetherian Z module. Because if it were so, then every submodule of it would be finitely generated, but we clearly obtained a submodule which is not finitely generated, right?
Yes, sir.
Yeah, okay. So what we saw here, you could also take various other examples, okay? Instead of taking Z adjoined with x1 up to xn and so on, you could just take, let's say, the ring of continuous functions on closed 0, 1, C01. This is a vector space over R. R is a field, hence in particular it has to be Noetherian because a field has exactly two ideals, right? So R is Noetherian. The real line, the field of real numbers is clearly Noetherian, but C01 is not Noetherian, that you can check. But these examples are, you have to work more for these examples. But yeah, you can always take very simple and trivial examples, okay. Anyways, so the upshot of everything we are doing here is this, that if R is a commutative Noetherian ring, then not every R module is Noetherian, right?
Yes, sir.
So
we found one submodule which is not finitely generated.
Yes, that means we found one module over R which is not Noetherian, even though R was a Noetherian ring. So that means that in order to obtain Noetherianness of the modules over that ring, as you know, the modules over a ring are basically sort of very, I mean, what should I, they are actions of that ring, right? So if you know the modules over a ring, you know the ring, sort of something like that. So so if even though the ring is Noetherian, the modules over that ring might not be Noetherian. So what do we need? So let us try to find out a condition so that if a ring is Noetherian, and the corresponding module over that ring is also Noetherian. That is, we want to put some extra condition on the modules, okay? And this is what the next problem is all about. So again, assume R is a commutative Noetherian ring, then every finitely generated R module is Noetherian. This is very easy. It will just take one line, but the statement is very important. This is true. So even
this is true, sir.
yes. So even though even though an arbitrary module over your Noetherian ring might not be Noetherian as a module over that ring, but if you take a finitely generated module over a Noetherian ring, then that finitely generated module has to be Noetherian. This is true, in fact, in much more generality, but we don't want to get into all this stuff. So this is true. So did I write false there? Yeah. So this is true, that if we take a finitely generated R module over where R is Noetherian, then indeed the module has to be Noetherian. Okay. So yeah, this is easy. So since R is Noetherian, okay, so I'll write this in. So let M be a finitely generated R module. Sorry, excuse me. So let M be a finitely generated R module where R is a commutative Noetherian ring. Then there exists an epimorphism, right? There exists a surjective module homomorphism. From some, okay, so yeah, from some R in onto M, right? You agree with this, right? Maybe you have seen this previously as well, I believe. If M, since M is finitely generated as an R module, there exists a surjective module homomorphism from some R in onto M, right? You are using the universal property of a free module here, right? You have studied free modules previously.
Oh, yes, sir.
So so we can just quickly go through this, right? This small argument. So suppose M is generated by as a module, M is generated by x1 up to xn. It's finitely generated. It is generated by some elements x1 up to xn. You can take the set x1 up to xn, and you have a canonical map from this into M, right? The inclusion map. And you also have a canonical inclusion of this into the free module, right? Generated by x1 up to xn. That is, you are treating x1 up to xn. In capital M, the x1 up to xn, all these elements have some relations between them. But in the free module generated by all these, you are treating x1 up to xn as mere symbols. Okay, there are no relations involved between this. You can just treat them as variables or just as symbols. Okay, so you look at the free module generated by x1 up to xn. This is precisely your Rn, right? And what does the universal property of a free module say? It says that this particular inclusion that you are taking here, that is, let me just use a different color. This inclusion that you are taking here, this blue inclusion, okay, this is universal among all such maps from the set x1 up to xn, okay, which means that any map from x1 up to xn to some module M you take, any map you take, that will always factor uniquely through this blue arrow, okay. So that means that any arrow or any any arrow or any map from this set x1 up to xn to any module M you take, that can always be extended uniquely to the free module, okay. That will always give you a unique map from the free module to M, okay. That is what your universal property says. And since this map since x1 up to xn are the generators of this map, this particular map is surjective. That is, you get a surjective homomorphism from Rn onto M. Okay, do you agree? You are just using the universal property of free modules. Okay, property.
Yes, sir.
And nothing else. So the upshot of everything here is that if M is a finitely generated R module, then there will exist a surjective module homomorphism from some Rn onto M. Okay, so let me just write homomorphism clearly. Oops. I don't know what happened to this. Yeah. Oh. Homomorphism, yeah. From some Rn onto M. Okay. Now, since R is Noetherian, hence Rn, which is R direct sum R n times is Noetherian, right, as an R module. This is also okay, right? Previously, yesterday in Harish's session, you might have seen this. I mean, maybe it was one of the problems that Noetherian, if suppose you take, so basically what it says is that if you take an exact sequence of R modules, so M to N, short exact sequence, M to N to P to 0 and 0 here, if this and Noetherian, then so is this, and conversely if N is Noetherian, then so are both M and P, right? Or maybe put in a different language, you know that if capital M or let's say N is Noetherian as an R module, then any submodule of it is also Noetherian, and every quotient of it is also Noetherian, right?
Oh, yes, sir.
Yes, right. And conversely, suppose N is an R module, M is a submodule, and both M as an R module and N mod M as an R module, both of them are Noetherian, then N has to be Noetherian. Okay. So using this fact, we know that the direct sum of Noetherian modules is Noetherian. Since R is a Noetherian ring, that means R is a Noetherian module over R, which means that R direct sum R is Noetherian, right? Why? Because R direct sum R mod R is just R, right? So R is Noetherian and R direct sum R mod R, which is just R, is Noetherian. That implies that R direct sum R is Noetherian, right? Right?
Yes, sir.
The point is that if R is Noetherian as a ring, then R power n is also Noetherian as an R module. Okay. So let me just write it as there is a complicated language to express this, but let me just write it like this, that as 0 to M to N to P to 0 being a short exact sequence of R modules implies that M and P are Noetherian if and only if N is Noetherian. This is just what we said in much short. Alternatively, we could also say that the collection of all Noetherian rings is something called a Serre subcategory of, I mean not Noetherian rings, Noetherian modules is something called a Serre subcategory of category of modules, R modules. But yeah, sorry for saying all this complicated language, but soon enough you'll see how important Noetherianness is. Anyways, I don't mean to confuse you, okay? So anyways, so Rn is Noetherian as an R module, right, Ravi?
Yes, sir. Direct sum of R modules will be Noetherian.
Not any R modules, direct sum of copies of R here, right?
Yes, sir.
Yeah. So since there exists a surjective homomorphism from R power n onto m, right? Right? That we observe because m is finitely generated, right? There exists surjective homomorphism, right?
Yes, sir.
And we know that if some module is Noetherian, then its quotient is also Noetherian, right? Any quotient of it is also Noetherian. Hence, okay. Hence, M is Noetherian as an R module. Any quotient of a Noetherian module is Noetherian. Again, you can use this short exact sequence thing that I have written in brackets. Any quotient of a Noetherian ring is Noetherian. A Noetherian module is Noetherian. Not only so, every quotient of a Noetherian ring is also a Noetherian ring. That is, if R is Noetherian, then any quotient of it by an ideal is as a ring, a Noetherian ring again. Okay. I hope you don't have any questions so far. If you have, you can always ask me. Okay. Is it okay?
Yes, sir.
Okay. So maybe I believe you are a bit shady on the free module part. Maybe you can just have a look at it. Okay. If you have any problem, you can let me know next week. Next week will be the last TA session, I believe, and then you can just let me know if you have any questions with free modules and all that. Free module is basically a module which admits a basis, and as you know that if you for vector spaces, if you take a basis and if you take any mapping of that basis into some other vector space, into some vector space, then you can always extend that map to a unique linear transformation from the uh, vector space to the other vector space, right? That is, you can extend any map to a unique linear transformation on the entire vector space, right?
Yes, sir. Linear transformation.
Yeah, if you know it, if you know the action of the map on a basis, then that map can be extended to a unique linear transformation on the entire vector space, right? That is what the analogous situation is happening here for free modules, because a free module is precisely a module which admits a basis, which is a direct sum of copies of the base ring. Okay, and it indeed has this but very nice universal property.
Yes, sir.
Yeah. Okay, so let me just end with this final problem. This is again very easy. I mean, we don't even need to do anything here. So assume just that V is a finite dimensional vector space over a field F. Let T from V to V be a linear map, and consider the canonical fx module structure on V induced by T. Right? We have seen this previously many times, that every linear endomorphism will endow an fx module structure on your vector space, so that your vector space is indeed becomes an fx module. Then we need to determine whether this statement is true or false, that V is a Noetherian fx module. Right? There is nothing to do here, just quick observations. Okay, this is true. So observations. Just one thing that I included this problem because I wanted to mention something. Maybe we did this. I remember doing this in maybe in week 7 or week 8 when we were talking about Noetherian rings. I don't exactly remember the week number, but there we talked about a very powerful or important theorem, which I just want to state once more. So that is your precisely your Hilbert's basis theorem, right? I don't remember if you are there, but what it says is that if R is a Noetherian ring, then Rx, that is a polynomial ring over R with in the variable x, Rx is also Noetherian. Okay, this is what
Yes,
this.
sir.
Yeah, so if R is Noetherian, then so is Rx as a ring. If R is a Noetherian ring, then Rx is a Noetherian ring. So first, so we make some simple observations here. Observation 1, F is a Noetherian ring, right? Every field is a Noetherian ring. Why? Because because the only ideals of F are the trivial ideal and the entire F, right? So that means that there are only finitely many ideals, which means that it will definitely satisfy the ascending chain condition on ideals. So F is a Noetherian ring. So what is observation 2? By Hilbert's basis theorem, Fx is a Noetherian ring, right? Since F is Noetherian, Fx is a Noetherian ring. What is number 3 observation? Number 3 is V was taken to be a finite dimensional vector space, right, over the field. Now,
Yes, sir.
now the Fx, now the scalar multiplication by elements of Fx, that is the Fx module structure on V, which is induced by T, that is an extension of the initial action of F on V, right?
Yes, sir. It will be also finite.
Yes, it will be a finitely generated module. So the Fx action on V is an extension of the F action on V, which original F action under which V was a vector space, or V is a vector space over it. So number 4 is, since V is a finitely generated vector space, I mean to say finitely, yeah, finitely, okay, so better to write, since V is finitely generated over F, hence V is finitely generated. As an Fx module, because the action is just an extension. So for the scalars, you can just take elements of F to be your scalars. You can take the same finite generating set, and the scalars are your elements from the constant polynomials. And finally, we are going to use our previous problem, right? Question 6, which says that if R is a commutative Noetherian ring, then every finitely generated R module is Noetherian, right? Right? So since, so yeah, so is it okay?
Yes, sir.
So using, so I just say using problem 6, it follows that we know that Fx is a Noetherian ring, and we know that V is finitely generated as an Fx module. So it follows that V is a Noetherian Fx module. Okay, and that basically finishes this problem. So if you have any questions, you can ask me. That's all from my side. So we can end the session otherwise.
Sir, the last slide and the 5th observation.
Yes, sorry. Yeah. What is your question?
Yeah. No, I got, sir. I just said.
Last slide.
I got, sir. I got. Thank you.
Okay, okay. Okay, so you don't have any other questions, right? So maybe then let's just stop the recording.